A 3.5 kilogram block is pushed along a horizontal surface by a force of magnitude 15 newtons at an angle of 40 degrees. The coefficient of kinetic friction between the block and the floor is 0.25. Calculate A, the acceleration of the block, and B, if the block starts from rest and reaches a speed of 1.05 meters per second, how far was the block pushed? Here's the diagram provided with the force F acting diagonal. Now, the first step is to draw the horizontal, because notice that this is an angle of depression acting down. Now, since F is diagonal, that means it acts both in the x direction and the y direction simultaneously. So this is my Fx, the amount of force acting in the horizontal or x direction. Likewise, my amount of force acting in y the weight of the block presses down. This is the force due to gravity, or weight, W. Next, the normal force is the force of the floor, the surface, pressing up against the block. So this is my normal force. Finally, since the block is being pushed to the right, again, since motion occurs right, friction resists or opposes the direction of motion. So this is friction. The mass was 3.5 kilograms. The force in newtons. Angle was 40 degrees. And mu, this Greek letter here with the little k subscript, represents the kinetic coefficient of friction, the roughness of the surface. And it's a unitless quantity. So finally, sum together all forces acting horizontally. Okay, well, that would be Fx, a positive Fx, and a negative F, because it points left, equals ma. Fx means F times a factor of cosine, and friction is mu times normal force. I'm just going to do two steps in one. I'm going to divide both sides by m. So I can isolate that acceleration. Now, we could just plug in numbers, but notice how, although our ultimate goal is to find A, we need to find N. Classic physics dilemma. So N, the normal force, is a vertical force. So to derive an equation for it, add together all forces, take into account their sign or their direction. Vertical equals mass, vertical acceleration. Looking back at my diagram, okay, well, here's a vertical force, here's a vertical force, and there's another. So I have a positive normal force because it acts up. I have minus weight minus Fy equals mass times 0. Since the block has no vertical motion, it doesn't move up and down, acceleration in the y direction is 0. N equals W plus Fy. Because again, my right-hand side is 0, so I add W and I add Fy to the other side. Good. Next, I replace W with mg. Fy is F sine theta. Here's my equation 2. Now, there's two choices at this point, and both are equally great. You can plug in all the numerical values here and obtain a numerical value for your normal force, or you could plug the expression of your normal force into your previous equation for acceleration. So our equation for acceleration was F cosine theta minus mu times normal force. But I replaced normal force with the expression mg plus F sine theta. This was all divided by m. Perfect. So F was 15 cosine 40 degrees mu. I'll use brackets. Again, the mass was 3.5. G, acceleration due to gravity, 9.8 or 9.81. Plus my force, again, that's 15 times sine of my theta, all divided by my mass of 3.5. My first term, once you type that into the calculator, gives about 11.5. I think it's like 11.49. And then once you find your second term, that's about 11.0. Again, that's 3.5 times 9.81. I add that to 15 times sine 40. This gives me about 43.976 and so on. And then I take that result, multiply by 0.25. Good. Yeah, and I get about 10.99. So 11.0 divided by that mass still. So I subtract those numbers, I divide by my mass, and then I get 0.143 meters per second squared is my acceleration. So that's how you approach a Newton's second law problem. And finally, part B is just a brief extension to this. Find how far the block moved. Okay, well, that's just the distance x. So I apply one of our kinematic equations. Let's look back. So notice how all kinematic equations contain A, and that's how they're linked to Newton's laws. Because usually you find A using Newton's laws, and then this allows you to use kinematics to find velocity or time or distance. Now, I'm not asked for time, and I'm never given time. So clearly, we'd like to use this kinematic equation since it doesn't contain t, but it does contain x, which is what we're trying to find. So finally, I'll use V final squared equals V initial squared plus 2ax. Subtract both sides by initial velocity squared. And that would equal 2ax. So we divide both sides by 2a. I guess I'll just write the rest here. They provided V final. They said it was 1.05. They said it started from rest. So V initial 0 divided by 2, and then our previously found acceleration. Once you type that into the calculator, you get about 1.10 divided by 0.286. So finally, we get a distance of 3.85 meters. Anyways, I hope that's a helpful tutorial on how to apply Newton's law. I just want to emphasize we only used a few memorized equations. We used one kinematic equation, and I just want to emphasize like the underlying theme of physics is that notice how there is a set in stone equation for friction. We can always use mu times normal force. But the situation is kind of a little unusual because normal force has no set in stone equation. It always changes from situation to situation. And because of that situation where it always changes from each scenario, that's why we have to derive our result. There are no shortcuts. So again, it's just a really interesting thing that happens that's really hard for students to grasp. They'll always say, okay, well, what's my equation for acceleration? Tell me the formula. And notice how there is no formula for acceleration in this case. It could be, in this particular instance, that's our expression for acceleration, but not always. So there is no set in stone formula for tension. It always changes from situation to situation. There is no set in stone formula for normal force. It varies depending on how many vertical forces act. So I just thought that's really interesting. So I hope that helps, and that's Newton's law with kinematic equations.